In this question, we will work with example 5.3 part E, but additionally we will consider the possibility of a temperature change in addition to the stress. In part A, we will discuss how a temperature change would affect the value of sigma y, and in part B, we will calculate the temperature change which would cause the copper alloy block to be on the verge of losing contact with the walls in the y direction. When we look at the example 5.3, we see that the rigid walls prevents deformation in the y direction, but material is free to move in x direction and also the z direction. So, in part A, we can say that epsilon y will be 0 and also sigma x will be 0. And also we have the information that sigma y is equal to lambda times sigma z. Using this information, we can say that if we increase the temperature, which is expansion, the material will try to expand, the value of sigma y will also increase, because even though the material tries to expand, the rigid walls will try to prevent this movement, so the value of sigma y will increase. Similarly, if we decrease the temperature, the material will shrink, and this will cause the value of sigma y to decrease. We are done with part A. Let's talk about part B. For part B, we will need the material constants, so we will write them first. From table 5.2, for copper alloy, we have Young's modulus is equal to 130 GPa, and Poisson's ratio is equal to 0.343. So, we will be considering the case in which the copper alloy block will be on the verge of losing contact with the walls. For this situation to happen, we should decrease the temperature. So the delta T will be smaller than 0. And at the exact point of losing contact, sigma y will be also 0. Let's calculate epsilon y. It is 1 over E times sigma y minus Poisson's ratio times sigma x plus sigma z plus alpha delta t because of the temperature change. We know that sigma y will be 0. And we know that sigma x is 0 from the beginning. So we have epsilon y as minus Poisson's ratio times sigma z over Young's modulus plus alpha delta t. And it will be also 0, as we can see from the observations. When we make some arrangements, we see that delta t is equal to Poisson's ratio times sigma z over Young's modulus times the thermal expansion coefficient. We know the values for these terms, so let's substitute them. Now, when we calculate, we can see that delta T is minus 11.99 degrees.